All right, welcome back everybody. Let's move on with Module 2. We'll take a look at pediatric weight estimation. That'll be a quick one. And then drug expressions. So quick question. What is the best way to determine a child's weight? It's an easy answer. Ask mom. Moms know. Dads, yeah, not so much. Moms know. However, there is a quick estimation you can use, which is useful for ages 1 to 10 years. You probably learned this one in school. 2 times the age in years plus 10 equals their weight in kilograms. It's just an estimation. It's just meant to get you into the ballpark of working with that kid. There's another calculation available. 3 times the age plus 7, and that's good up to about 13 years. So pick whichever one you want. This is the one that's kind of the gold standard in the province to get you into that neighborhood. But like I said, if you're not sure or mom is available, ask mom. Moms know. All right, that one was easy. Let's move on to drug expressions. Drugs are prescribed or ordered in weight. So we deal in milligrams, micrograms, and sometimes grams. Those are measures of weight. However, our drugs are suspended in a solution. They're a fluid. Therefore, we are administering a volume of fluid that happens to have a certain weight of drug suspended in it. So what that means is we have to work in 2 areas. We have to work in weights, and we also have to work in fluid volumes. And that's where people sometimes get hung up a little bit. Most of our drugs are provided in familiar ampules or preloads, and we know what they are. We know how much drug is in, how much fluid in that particular packaging. However, there is a new reality in the 21st century. They're called drug shortages. They're becoming a frequent reality. There's probably drug shortages going on right now. Paramedic services and hospitals and doctors and everybody else for that matter may be required to purchase their drugs in alternate packaging or unfamiliar concentrations. They may have no choice. The most desirable packaging may not be available, and they have to buy something alternative. In these cases, attention to your math detail is going to be critical because you may not be getting the amount of drug you think you are in a particular volume of fluid. So you have to be careful with it. And this is becoming a common reality, and it's probably here to stay. There's no suggestion that drug shortages are going to suddenly resolve and we'll be able to buy absolutely everything we want. So we'll have to take a little bit of care to make sure that we're delivering the drug we think we are. Let's take a look at concentration. Concentration expresses the amount of medication as a mass or a weight in a volume of solution. So it's usually expressed as mass of the drug in a volume of solution. So the weight of the drug may be expressed in grams, milligrams, or micrograms. As I said before, the volume of fluid is typically measured in milliliters, or sometimes called cc's. Milliliters and cc's are the same thing. So let's look at an example. Glucagon is supplied as 1 milligram of powder, which you go ahead and reconstitute using 1 milliliter of solvent. Once you're finished with it and you draw it back up, you will have 1 milligram of glucagon in 1 milliliter of fluid. That one you probably already know from school. It is what it is. Let's look at one that you may not be as familiar with and requires a little bit more math. Lidocaine is supplied 100 milligrams in a 5 milliliter preloaded syringe. You're probably already familiar with that. Using simple math, we should be able to calculate how much drug is present in 1 milliliter of solution. So this sounds like we got a little division coming our way. let's see what we need to do. 100 milligrams in 5 milliliters. If we divide both sides by 5, we'll end up with 20 milligrams per milliliter of fluid. So now we can do additional math from here to figure out how much drug we need to give to a particular patient. So according to our ALS-PCS, an 80 kilogram patient in cardiac arrest should receive how much lidocaine? And in case you don't know it off the top of your head, hopefully you do though, lidocaine dosage for an adult is 1.5 milligrams per kilogram. Ooh, sounds like we got more math coming. So let's see. In the brackets on the left-hand side, 80 kilograms times 1.5 milligrams, right out of the protocol, equals 120 milligrams. That patient needs 120 milligrams of drug. The problem is we need to figure out how much fluid will contain that drug. In the brackets on the right-hand side, I've divided the desired 120 milligrams by the concentration, which we now know is 20 milligrams per milliliter. That equals 6 milliliters. So there's our result. According to the ALS-PCS, an 80 kilogram patient in cardiac arrest should receive 120 milligrams of lidocaine, which would be in 6 milliliters of fluid. Sounds like you're going to need one preload and then a little bit of the next one. All right. Your turn. We're going to do this again. There's 6 questions for you to work out. Determine how much drug is provided per milliliter in each case below. Some of them are really easy. Some of them are a little bit more tricky. Go ahead and press pause. Just like last time, I'll be here waiting when you're done. Then we'll take up the answers and see if we agree. All right, welcome back. Let's see how you made out and if you agree with my answers. Here's all 6. Diphenhydramine supplied 50 milligrams in 1 milliliter. Well, that one was easy. It was already given. 50 milligrams per milliliter is the concentration. Fentanyl is supplied 100 micrograms in 2 milliliters of fluid. So the concentration is 50 micrograms per milliliter. Do you see what I did there? I just divided both sides by 2 to get 50 in 1 milliliter. Let's move on. Midazolam is supplied 10 milligrams in 2 milliliters of fluid. Concentration is 5 milligrams per milliliter. Same thing, I divided each side by 2 to get down to the concentration per milliliter. Number 4, Ventolin for nebulization is supplied 2.5 milligrams in 2.5 milliliters. How am I going to figure this one out? Looks like I need to divide both sides by 2.5 and I'll get down to 1 milliliter. Concentration is 1 milligram per milliliter. You probably already knew that one. All right. Here's one's a little bit more tricky. It requires moving a decimal point, so hopefully you get it right. Atropine is supplied 1 milligram in 10 milliliters of fluid. If we divide both sides by 10, we'll end up with 0.1 milligrams of atropine per milliliter. Finally, number 6, dextrose is supplied 25 grams in 50 milliliters of fluid. Divide both sides by 50, I end up with 500 milligrams per milliliter of dextrose. Hopefully you didn't find those too hard because they really shouldn't have been. Let's take a look at serial dilution. It's based on how much solution in milliliters into which 1 gram of medication is diluted. So think about that again. we're dealing with 1 gram of medication. We want to know how much solution that 1 gram is diluted in. So classic example, and I'm going to use it, is our 2 flavors of epinephrine. Where 1 gram of epi has been diluted in 1,000 milliliters of solution, we have 1 to 1,000 epi. So there's your IM injection of epi for anaphylaxis or something like that. Second one, where 1 gram, we're dealing with the same 1 gram of epi is diluted in 10,000 milliliters of solution, we have 1 to 10,000 epi. So there is your preload for cardiac arrest, 1 to 10,000 of epi. We're dealing with the same weight of drug. It's just the amount of dilution we're using. So let's look at this a little closer. Here's our epinephrine, 1 milligram in 1 milliliter ampule. So just like down the bottom corner there, that's what we're talking about. 1 milligram in 1 milliliter. What is a serial dilution? So, because I know serial dilution is working with a full gram, we need to multiply our weight of drug by 1,000 to get to 1 gram. So 1 milligram times 1,000 equals 1 gram. So I'm there. Let's do the same thing to the volume because we're going to bring things up both ways. Multiply 1 milliliter times 1,000 because we do the same thing to both sides. And that equals 1,000 milliliters. So we end up with 1 gram in 1,000 milliliters or 1 to 1,000. And you already knew that. I'm just making sure that you know the math behind why it's 1 to 1,000. So it's your turn again. This is an easy one. Epinephrine is supplied 1 milligram in a 10 mil preload. What is the serial dilution? So we want to do the same thing we just did back here, but this time we want to use 10 mils of fluid. So it's a more diluted drug. So you go ahead, press pause. I'll be waiting when you come back, and we'll see if you get the right answer. I know you already know it. I want to know if you know how to get there. All right, welcome back. Let's see if we agree, shall we? Here's my answer. Just like last time, epinephrine is supplied 1 milligram in a 10 milliliter preload. I'm going to multiply both sides by 1,000 because my goal on the weight of the drug side is to get to 1 gram. 1 milligram times 1,000 is 1 gram. Do the same to the volume. Multiply 10 milliliters by 1,000. I get 10,000 milliliters or 1 to 10,000. Again, I know you already knew the answer. I want to make sure you understand the math to get there. Finally, percent concentration. This one's kind of fun. Based on the fact that 100 milliliters of water weighs 100 grams. Remember that one. 100 milliliters of plain old boring water weighs 100 grams. So, the weight of a medication suspended in the solution can be expressed as a percentage of the weight of the total solution. So, if 100 milliliters of water weighs 100 grams, but I've got some drug that happens to be dissolved in that water, then I can do some math and I can figure out what percentage of that weight is drug and what leftover percentage is just water. So let's look at an example. A liter bag of D5W is 5% dextrose in water. Let's figure out how we get there. If 1,000 milliliters of water weighs 1,000 grams, And in D5W, we know that 5% of that weight is dextrose. And likewise, 95% of that weight is just plain old water. The 5% that's dextrose is what we're interested in. Then 50 grams of dextrose is present in the liter bag. So how did I get to that 50 grams? Well, I'm using my 1,000 grams, because we know that 1,000 milliliters of water weighs 1,000 grams. All I'm doing is I want to know what 5% of that 1,000 grams is. And that's 50 grams. It's that easy, folks. Here's another example. Let's use a little bit thicker dextrose. Dextrose is supplied 25 grams in a 50 milliliter preloaded syringe. Again, here's our preload for our hypoglycemic patient. Start your IV, give them some sugar, wake them up. Let's figure out our percent concentration. Multiply 50 milliliters by 2 to get 100 milliliters, because we know that 100 milliliters weighs 100 grams. Ensure that the drug is expressed in grams, which it is. That's what we're after. Multiply 25 grams by 2. The same as what we did to the fluid volume we want to do to the weight to get 50 grams. And then we end up with 50 grams in 100 grams of water. 50 grams of drug in 100 grams of water means 50% of the weight is drug, or it's a 50% solution. I guess that's why they call it D50. Huh. All right, your turn. We're going to do this one more time. Consider our dextrose medical directive. Dextrose is supplied 25 grams in a 50 ml preloaded syringe. So we know that. We know that's D50. We know it's 50%, 25 grams and 50 milliliters. If you discard half the volume and then draw up normal saline, ooh, what is this sounding like? This is sounding like we're treating a hypoglycemic patient who's under 2 years old. Again, stick this one in your back pocket. If you discard half the volume of that preload and draw up normal saline, how much dextrose do you now have in the syringe, and what is the percent concentration? Hit pause, figure out your answer, and then we'll see if we agree. All right, welcome back. Let's see if we agree. Dextrose is supplied 25 grams in a 50 milliliter preloaded syringe. If you discard half the volume, you will be left with 12.5 grams in 25 milliliters of fluid. All I did was divide both sides by 2 because I got rid of half of it. So, 12.5 grams will be in 25 milliliters of fluid. Now, if we drop normal saline, think about what we're doing here. We're adding fluid volume, but we're not adding any more dextrose. So instead of 12.5 grams in 25 mils, we're going to end up with 12.5 grams in 50 mils. Aha! We're getting somewhere here. We've had a big change. We've had a change in our percent concentration. You now have dextrose, 12.5 grams in 50 milliliters of fluid. Multiply 50 milliliters of fluid by 2 to get 100, because we know 100 milliliters weighs 100 grams. Multiply the 12.5 by 2 to get 25 grams. Oh my God, 25% solution. Hopefully you got that answer right. You probably even used a shortcut to get here, and that's okay. so long as you understand the math and you understand how the shortcut worked. There's your answer. All right, that's the end of Module 2. When we come back in Module 3, we're going to discover single dose calculations. Hurry back.